So lesson 2.6 is all about advanced factoring, and I know the title is really scary, and when I tell you that I really like this lesson, that might scare you too, but don't let it. Advanced factoring just means higher order factoring. So the first thing you guys, and you've already seen this, is the sum and difference of two cubes pattern. So if you have the sum of two cubes, it factors like so, and the difference factors like so. They're very similar patterns, the only difference is where the negative is located. So it's plus minus plus for the addition, and minus plus plus for the subtraction. So we're going to completely factor and then go ahead and solve for all real and complex solutions in this particular question. So it's the sum of two cubes. I always told my kids in Algebra 2 to tell me who the a and the b are. So it's the cube roots of both of these. So a is x and b is 2. And when I substitute those values into the pattern, I have x plus 2 times x squared minus 2x plus 4. And they want me to solve for everything. So the first factor is super easy to solve. I just get x equals negative 2, but hold on to him, he's part of the answer. Now the other part is a quadratic, and you remember your algebra algebra 2 teacher telling you the reason we like that factoring pattern is because we knew it couldn't factor any further, but that's kind of bad news today because that means his solutions are going to be not pretty or imaginary. So we can do quadratic formula. You could also think about completing the square. I kind of think I'm in love with completing the square all of a sudden. I don't know. I like to solve through completing the square. It's just one of those things I like. So I'm going to move the negative 4 to the other side. If you just love quadratic formula, you go right ahead. Half of negative 2 is negative 1. Negative 1 squared is 1. So then we're going to factor x minus 1 quantity squared. And then negative 4 plus 1 is negative 3. And then when I go to solve this, because now I can square root, plus and minus square root of 3 with a negative 1 means it's I squared to 3. And then my final answers are 1 plus and minus I squared to 3. So I just found a total of 3 solutions. The real solution of negative 2 and the imaginary solutions of 1 plus I squared to 3 and 1 minus I squared to 3. Okay, the next question. Cubic pattern again. The a is a 3x. The cube root of 27 is 3 and x is 3. And the b is a 1. Remember the negative is built into the formula. So using my formula, a minus b, this is the part my kids last year sometimes would mess up. A squared would be a 9x squared plus a times b plus b squared. And then I'm going to solve the easy one first. I can do this in my sleep. It's a 1/3. Hold on to that because he is your only real answer. Now the quadratic needs to be solved using another method. I'm thinking completing the square is a terrible idea on this one because the a value is not a 1. I would have to divide everybody by a 9. No thank you. So let's resort to quadratic formula. Negative 3 plus and minus b squared is a 9 minus 4 times a times c, and yes, it's going to be imaginary, and that's what's supposed to happen. 2 times a. So negative 3 plus and minus, oh goodness, 9 minus 36 is negative 27. I always do silly math, so I'm trying to concentrate. Negative 27 breaks into 9, negative 1, and 3. So we're going to say that's negative 3 plus and minus 3i squared to 3 all over 18. And that's no good because we know that the 3, and the 18 can all be divided by a 3. So my final answers are negative 1 plus and minus 1i squared to 3 all over 6. And those are the 2 imaginary answers. Here's my 1 real answer. I found all 3 answers. Oh goodness, more. Alright, so this time, I don't know if you noticed this, but there is a common factor of 8 that I could actually divide by. So x to the 3rd power minus 8 equals 0. Now this looks really similar to the first problem we did. The only difference is this is the difference of x to the 3rd minus 8. So factoring is, hello, try again, x minus 2, x squared plus 2x plus 4. Now I know you feel like this should be really close to the same answer. Kind of is. I can solve this quadratic with whatever method I want, and you know I'm kind of in love with completing the square, so I'm going to do that again. It's very, very similar to the last question. or the 2 questions ago, I should say. Because we're still going to get equals to -3. I'm still going to square root. The difference here is I'm going to end up subtracting 1. So I'm going to cheat -1 plus and minus, pull out the I, square root's a 3. There's my 2 complex answers. Alright, still would have got those answers had you never factored out the 8 or divided by the 8. You just would have had more math to do than I did. So here, the pattern is, okay, A is 3x plus B is 5. A squared is 9x squared minus A times B plus B squared. Alright, looks like completing the square is not a good option today for my quadratic component. Not for that problem. So there's my real answer. And when I do quadratic formula on this problem, let's see, opposite of B, B squared is, let's see, 225 minus 5 times 9 times 25, whoops, all over 2 times A. And I'm going to grab my calculator because it's Friday and I'm tired. Ooh, that's interesting. In the radical, the discriminant comes out to -900, which is kind of awesome. -900 is, I think it's 30i, so 15 plus and minus 30i over 18. All of those coefficients can be divided by, oh goodness, a 3. So we have 5 plus and minus 10i all over 6. So there's my 2 complex solutions. I really have a bad habit of doing this. You're supposed to say x equals in front of those quadratic answers. I always forget that. Okay, another higher order factoring technique was factor by grouping. You will notice that these problems all have 4 terms, and you did do this in Algebra 2. So we group the first 2 and we group the last 2, and we think about separating them into 2 groups. So the first group has a common factor of 2x, leaving me with x minus 5. And then the second factoring, I'm going to take a -1 out, because what I need to have happen is the parentheses need to match. And now you will notice the parentheses do indeed match. So the x minus 5 is going to come out in front of the whole problem. And when I remove the x minus 5s, I'm left with a 2x and a -1. And now I have a pretty nice, easy thing to solve. So this first answer is going to give me x equals 5, and this guy will give me x equals 1/2. Done and done. Okay, the next problem, group 1, group 2. So taking an x squared out of the first group, I'm left with x squared minus 4. I'm going to take a -16 out of the last group. That's going to give me an x squared minus 4. Again, if the parentheses don't match, you need to revisit what you've done, because it's not right. So I'm going to take the x squared minus 4 in front of the whole problem. And when I remove the x squareds minus 4, I'm left with an x squared minus a 16. And then when I solve these, they are quadratics, but they're easy to solve quadratics. I would just add the 4 and square root. So this first guy gives me a plus and minus 2. And this second guy gives me a plus and minus 4. So I get 4 answers, and that doesn't surprise me, knowing that that was a degree 4 polynomial. Okay, more factor by grouping. So, first group, take out an x squared. That leaves you with x minus 2, and then I'm going to take out a positive 5. Leave the positive, or the plus sign in front of it. It helps you with the factoring later. Oh gee, what do you know, x minus 2. So I'm going to take the common x minus 2 out of the whole problem. Leaves me with x squared plus 5. So this guy is super easy to solve, x equals 2. But my last quadratic, so the second quadratic, when we solve that, we would first subtract the 5, and then when I square root both sides, I'm going to get plus and minus. I would be able to pull out an I, and then square it to 5. Okay. The next problem, same technique. I can factor out a 3x from my first group, leaving me with x squared minus 3. And then there is nothing to factor out here, but you got to factor something out. So we're going to factor out a plus 1, which doesn't change the x squared minus 3 at all. Now when I pull the common x squared minus 3 out, I am left with 3x plus 1. And let's see if I can solve this quick. I would add the 3 and then square root, so we have plus and minus square root of 3. And then this is a linear solving problem or equation, so negative 1/3. So 3 answers there. And again, doesn't surprise me. The degree of that polynomial is 3, so I should be finding probably up to 3 answers. Now this is probably a new technique to everybody. We're going to factor using substitution. And in calculus, you would refer to this as U substitution, because they constantly use U as their substitution variable. But the idea is you're going to have a really gross factoring problem, and we're going to scribble out the gross part and make it more pleasant to look at. So 2x minus 1 quantity squared plus 2x minus 1 minus 6. It would be really awesome if these 2x minus 1s were just something. So what we're going to do is we're going to let U represent the quantity 2x minus 1. So everywhere I see a 2x minus 1, I'm going to call it U. So this is really U squared plus 1U minus 6. And I can factor this. This is a baby factoring problem. So we get U and U, and then multiplies to negative 6, adds up to positive 1. So how about a plus 3 and a minus 2? So solving this problem, I get U equals negative 3, and I get U equals 2. But we're still not done. Because remember, U is not really U. U is 2x minus 1. So what I'm going to say is 2x minus 1 equals negative 3. And 2x minus 1 equals 2. And that I can solve. So I'm going to add the 1, divide by 2, and I get x equals negative 1. I'm going to add the 1, divide by 2, and I'm going to get x equals 3 halves. And trust me, the alternative to solving that equation was not great. That was a really slick method. So the hardest thing I think about U substitution is trying to figure out what U should really represent. And if you know that you have a quadratic, always look for the middle term, the middle weird term, because he is supposed to be the generic variable. The b term is always the x instead of the x squared or the constant. So he's the place you look. So keeping that in mind, let's look at this next example. I have never been able to factor something with those weird, funky exponents, but again, I instructed you to look at the middle term, the b term. What if we let U represent x to the 1/3 power? Well, x to the 1/3 power squared would be x to the 2/3 power. So this is a U squared. This is a U, and a 12 is a 12. So we're going to go ahead and factor this. And I get U minus 4, U plus 3. So officially, my answers are U equals 4 and U equals negative 3. However, U is not U. U is really an x to the 1/3 power. Okay, so to solve an equation with x to the 1/3, you're supposed to raise it to the reciprocal power on both sides. So 1/3 reciprocal is 3 over 1, or 3. Well, same thing over here. Whew. So my final answers are 4 to the 3rd, which is 64, and 3 to the 3rd, which is 27. Yahoo! Again, I know it's hard to figure out what U is supposed to be. Whoa, sorry. Grabbing the window. Look in the middle. The middle term is x to the 1/4 power. He's your U. If I were to square him, I would get 2/4, or 1/2 power, so this is U squared. This is minus 5 times my U, and then plus 6. We are going to factor this into U and U. Minus 3, minus 2. So at first, I get U equals 3 and U equals 2. But U is not U. U is really an x to the 1/4 power. So if I raise everybody, I'm just going to cheat and do it this way, to the 4th power. Sorry, it's hard to write. 3 to the 4th power is 81, and 2 to the 4th power is 16. My two answers are 81 and 16. Again, I know it's really difficult to figure out what U is supposed to be. Look at the middle term. The middle term is x to the negative 2. He is going to be the U. If I were to square that, I would get x to the negative 4, and that's what I see here in my first term. So that's 3U squared plus 2U minus 5. Factoring that quadratic takes a little more care than the last couple problems. Let's see, I think we're going to subtract 1 and then we're going to add 5, and that'll add up to a 2 in the middle. So, u is negative 5/3. U is also equal to 1, but u is not u. U is an x to the negative 2. Now, we don't typically solve equations like this, but a couple of different ways to think about it. We're supposed to be raising it to the reciprocal power. So, the reciprocal of a negative 2 is a negative 1/2. A little strange. The negative 1/2 power is, well, we all know what a negative exponent does, is it takes the reciprocal of the number, or the fraction in this case. A 1/2 power square roots it. So what we have is the reciprocal of this, which is, ooh, let's see, I feel like I messed something up here. I think we have a problem, because we're not going to be able to square root that number. Let me just mess around with something for a second. Yeah. I can't remember if this section said they wanted imaginary numbers or not. It's okay. We'll pretend they want imaginary numbers. So the reciprocal of this would be negative 3/5, and then we're square rooting it. Now, technically, the answer would be plus and minus, and then we would pull an I out of this. We'd have square root of 3 over square root of 5, and we're not supposed to have radicals in the denominator, so then we would rationalize by multiplying top and bottom by the square root of 5. So technically right now I have two answers of I square roots of 15 all over 5. That's the first two answers. This is much uglier than I thought it would be, sorry. And then this problem, well, it's a little better. The reciprocal of 1 is 1. And then I'm going to take the square root of 1, which is 1. But remember, square rooting an equation means it's positive and negative 1. So if you will notice, we found 1, 2, 3, 4 answers. Technically, I should have, because even though it's weird, it's to the negative 4th power, there are 4 answers there, 2 of which were imaginary or complex. Alright, last question, I believe. The middle term, if I look at the variable component, it's strange. It's x squared times the square root of x. I think I'm going to rewrite that a little simpler. I know that's the same thing as x squared times x to the 1/2, and then exponent properties say when I multiply the bases, I'm supposed to add the exponents. So 2 plus 1/2 is 5/2. So that's really x to the 5/2. And then think about this. If I was to square x to the 5/2, I would get x to the 5th, which is the variable component of the first term. So I do have 2u squared plus 4u minus 6. I notice this quadratic could all be divided by a 2, so I'm going to take care of that. And then when I solve this quadratic, I'm still not done, because u is x to the 5/2, and we are going to raise to the reciprocal exponent in just 1 minute. So, raising everything to the 2/5 power. We don't have to worry about i's, because 2/5 power is 5th rooting it, and we're allowed to 5th root a negative answer. Geez, I don't know what answer I'd like here. X equals negative 3 squared, 9, 5th root of that. Technically the answer is the 5th root of 9. Gross. And then here, 1 squared is 1, 5th root of 1 is 1. I guess I like those answers. So, I don't know. Strange answer. I think the homework is a lot easier actually than some of the notes questions that we've done. So, best of luck to ya.